configuration, and we just wrote the 6 of the main atom.
Okay, so try a few more just to get the hang of it. We'll start with aluminium. The atomic number of aluminium is 13, and then you can do yttrium. Atomic number of yttrium is, I guess, 39. Do these two, then we will go on to the next. What you have to remember, you have to remember this formula, right? Ns n minus 2 f n minus 1 d and np. And if you're writing the condensed electronic configuration, then you have to remember this sequence: helium, neon, argon, krypton, xenon and radon. Xenon and radon. The sequence that you have to remember was 2, 8, 8, 18, 18 and 32, right? 32.
Yes, sir.
What will this do? Helium will go for 2, then you have to add 8,
8.
then another, sorry, if you add 8,
I
then
added
this
to
will be 10.
18,
If you add another 8, this will be 18. If
36,
you will add 18, then it will be 36. This will
54 and
be
86.
54, and this will be 86, right?
86.
This is 1, this is 2, 3, 4, 5, and 6. So aluminium 13. What would you use here? Which noble gas?
So neon.
Neon. Okay. Then after neon,
Sir, after neon we will have so 3s2
right? 3s2.
and so aluminium was
13. Aluminium is 13.
13. So
You have
3.
only one electron left.
Yes, sir. 3s2 and
Okay, you have written
3p1.
Yes, right. 3p1. Thanks so much of time. You have chosen 3. If you put 3 here, 3 minus 2, 1, 1f does not exist. You put 3 here, 3 minus 1, 2, 2d does not exist. So we will not take these two, we will take only these np. Okay, fine. For yttrium, 39. Which noble gas?
So krypton.
Krypton. Okay.
And so then krypton and 5s2.
5s2.
And sir 4d1.
4d1. Correct. Okay. Now we will learn about the electronic configuration of ions. Electronic configuration of ions. Okay.
Yes, sir.
What is an ion? First of all, tell me.
So any atom which loses or gains energy by the exchange of electrons forms an ion.
Forms an ion, right? But here, what we will specially learn about the electronic configuration of a cation. And how do we form a cation? We have any element, for example, A, then it loses an electron and it gives us A plus, or A, it loses two electrons and it gives A 2 positive, right? So these
Yes.
are the cations, and we will learn about the electronic configuration of cation. The important part to remember here is the electron is taken out from the outermost shell. Which shell?
Outermost shell.
Outermost shell. And how will we define this outermost shell? How we will recognize it? N will be maximum, right?
Yes, sir.
The shell whose N is, that is principal quantum number, is maximum, that shell, the electron from that shell will be taken out. Okay. So
Yes,
for
sir.
example, give me the electronic configuration for Na plus. Na plus. So when you are asked for the electronic configuration of Na plus, what you will do? You will first write the electronic configuration of sodium, Na. What will the electronic configuration of sodium? 1s2, 2s2. What is sodium? Sodium is 11, right?
Yes, sir.
You write,
Can't we do it in the condensed form?
we can do it in the condensed form.
Because if we see, we'll get the electronic configuration of argon of neon only when we consider N plus.
Yes. Right.
Because the sole
And then,
purpose of giving electrons is to establish an inert gas state.
right. Then after neon, what should I write? For Na,
So
that is 11. Not for sodium plus, for Na.
for Na, so Na will be 3. So 3s1.
3s1, right? So Na plus
Yes.
would be, we will remove
So
this
Na plus
3s1
will
and you
be
will write,
Ne.
but you cannot write just Ne. You can write this
Yes,
Ne,
sir.
it will be just Ne, but you have to expand it now. How will you write it? 1s2,
So
furthermore, 2s2, then
it's to 2s2,
2p6,
2p6.
right?
Yes, sir.
Initially, you see here, right? This N is maximum, this 3 is maximum here. What does neon represent? Neon represent this electronic configuration in condensed form, and in the expanded form we see that the maximum N is 2, but when the atom sodium was present, the maximum N was 3,
3.
and this is the outermost shell, and this is the electron which is taken out, right?
Yes, sir.
Correct or not?
Yes, sir.
Now do some examples for Fe2 plus. Fe2 plus, right? What is the electronic, what is the atomic number of Fe? It is 26. So how will we write it? Which noble gas?
So the noble gas will be argon.
Argon. How
And
many
sir,
electrons left? Argon is 18.
sir, 8 electrons are left to be filled, and so
Not 8 electrons. Is 8 electrons. 8 electrons.
yes, sir. And we'll get sir, argon is the third in the list. So
Third in the list,
4
right?
4s2,
4s2,
3d
3d
3d 6.
6,
Yes, sir.
right? But even though 3d, the subshell 3d is
So
higher
but
in
we'll take
energy
it out
than
from
4.
4s because 4 is greater than.
Yes, the electrons will be removed from 4s subshell. So the
So sir, we'll just
electronic
have
configuration will
argon
be
3d6.
argon
3d6.
3d6, right?
Yes, sir.
But what will happen if someone asks you what is the electronic configuration of Fe3 plus? Now what will you do?
So if E3 plus, so then we'll remove one electron from 3d6,
Right, right. So this will be just a argon
3d5.
3d5, right?
Yes, sir.
Okay. So let us do some more.
So 1 minute.
Yes. Okay. Okay. Sorry.
Done, sir.
Done.
Yes, sir.
Okay. Let us do some example. Let us do Ni2 plus calcium 2 plus and let's do titanium 2 plus. Let me know if you want the electronic configuration of any one of the following.
Yes, sir. So what about atomic numbers?
Atomic. Okay, fine. Atomic number. You need atomic number. I'm giving the atomic numbers for the atoms. Okay.
Yes, sir.
This is nickel is 28, calcium is 20, titanium is 22.
Yes, sir. Done.
Done. So I guess argon will be common in all three of them, right?
Yes, sir. So for first part, we'll get AR 3D8.
AR 3D8, right?
So second will be electronic configuration of argon.
Right.
Third will be AR 3D2.
3D2. Right, correct. Now write a note. What happens if you have a choice between the S subshell, P subshell, D subshell, and F subshell? What if all these four are present and all of them have the maximum principal quantum number? Then how will you choose? What you have to write it is that the order for electron release from the subshell provided that each of them has the maximum n. What is n? Principal quantum number. So what will be the order? The electron from the F subshell will be released most easily, then the D subshell, then the P subshell, and then the S subshell.
Yes, sir.
Note this down. I will look for an example. Yes, I got an example. For example, 10. For example, 10. This is Sn. This is 10. The atomic number is 50. The atomic number is 50. The electronic configuration will start from krypton. To start from krypton, it will be having 5s and 5p. First, let me write 4d10. The subshell will be full, then 5s2, then 5p2. So if we have 10 plus 2, that is Sn plus 2, this will be equal to krypton 4d10 5s2.
Okay, sir. Got it.
Got it?
Yes, sir.
Okay. So we are done with electronic configuration, writing of electronic configuration. The new
Yes, sir.
concept that we will start, and you have got a bit about this earlier also. The concept is Pauline's exclusion principle. Pauline's exclusion principle. What does this state? The statement we have covered earlier also. This statement, what does it say? It says that no two electrons can have the same set of all four quantum numbers. All four quantum numbers. No two electrons can have the same set of all four quantum numbers. What does this implies? This implies that in an orbital,
Yes, sir.
There can be only two electrons. There can be only two electrons, right? Because any electron can have the same principal quantum number. For example, the principal quantum number is 1. It can also have the same azimuthal quantum number. Here it will be 0. It can also have the same magnetic quantum number. Again, this will be 0. But the two electrons must have two different spin quantum number, either minus half or plus half, right?
Yes, sir.
These three can be same in a subshell, but the spin quantum number, the last quantum number, would always differ, right? Hence we
Yes.
show the, if we have p subshell, then we show the subshell as this and the other electron as this, and each orbital in p subshell, which compromises of 3 orbitals, have only 2 electrons in each orbital, right? So if somebody
The
asks,
arrows represent electrons.
yes, arrows, this either half arrow, or you can also write as complete arrows. There's no problem in that. It is just about the preference, how you want to write it. Both of them are same thing. Okay.
Yes,
So if somebody asks you how many electrons, I have asked this question previously also. I'm asking, just changing the subshell. How many electrons can the p orbital accommodate? What would be the answer?
so p orbital, sp second one. So sir, it can accommodate 8 electrons,
Oh my god, p orbital.
6 electrons, 6 electrons.
Again wrong. See, where if somebody says p orbital, then remember this word orbital, right? And how many electrons can an orbital accommodate? Only 2 electrons,
So only 2 electrons.
irrespective of what the subshell is. But if somebody changes the question and asks you how many electrons can the p subshell can accommodate, then the answer would be 6 electrons, right? But
Oh,
you see the difference? But we didn't ask p subshell, we asked about p orbital.
yes sir.
Now see any one of the orbital in the p subshell, take this orbital. How many electrons it can accommodate? Only 2 electrons. So irrespective of what the subshell is, the orbital always and always it will accommodate only 2 electrons. In an orbital, there can only be 2 electrons. Or a better wording would be, there can be no more than 2 electrons. Okay, got it?
Yes sir.
So this was the Pauline's exclusion principle. Note it down. Have you noted this down? If you
So
not,
just
then note
writing
it
the
down.
question.
Okay, write the question. Note this down.
Done sir.
Done. Okay.
Yes. 1 minute sir, 1 minute.
Okay.
I missed the definition. I went into writing the question.
If you are on it, then write another point also. Wait a second. Write another point. Not there can be no more than 2 electrons with opposite spins.
Done sir.
Done. Okay, great. Next thing that we have to learn is Hund's rule of maximum multiplicity. Hund's rule of maximum multiplicity. Let us see the statement first. What does this say? It says that the pairing of electrons in a subshell can only take place after each orbital is singly occupied with same spin. What does this mean? Let us say, for example, in S subshell, we don't have any choice since S subshell can have only one orbital. Hence, an electron will fill this orbital, and the next electron can come and just fill the other vacant site, right?
Yes, sir.
But for P, we have a choice, right? You filled an electron. Now you can either pair this electron and you can add the next electron in the same orbital, right?
Yes,
Or
sir.
we have another choice that we can fill the next orbital with the same spin, right?
Same spin.
If you're filling in the same orbital, you must have the other electron with opposite spin due to the Pauline's exclusion principle, right?
Yes,
But
sir.
what happens is if you fill in the same orbital, this will cause repulsion, right? Both the electrons are of negative charge,
Yes. Yeah.
right? And they will cause repulsion. That is why Hunt came with a rule that the electrons will be paired only after all these orbitals are singly occupied. Now, when the fourth electrons comes in, now it can pair. Usually we pair with the first orbital, but it doesn't matter. You can pair with any of these three orbitals. Okay. What
Yes.
is the reason that this pairing does not take place in the first time? It is because it is due to the repulsion. But now when you have the fourth electron, you don't have any choice. So you have to compensate the repulsion, kind of collateral damage, and you have to pair these further electrons. Okay. Now what will
Yes.
happen in D subshell? In D subshell, you will have 1, 2, 3, 4, 5. All these must be first singly filled. Hence, if you have a configuration of D5, all these will be singly filled. But if we have D6, one more electron, then the pairing will start. Got it?
Yes, and so when we are filling the arrow which faces downwards, the anti-clockwise spin, so we have to pair it from the starting, or we can put it
No,
anywhere.
you can pair it anywhere. For the fourth electron, this configuration.
And sir, like we cannot do it this way that we first complete the first shell that we are putting in clockwise spin, then an anti-clockwise spin, then again a clockwise spin. We have to first complete the.
First of all, you have to singly occupy, you have to singly fill the orbitals with same spin.
So, sir,
Okay?
the first repulsion, so the case in which we will have repulsion, we cannot do it that.
No, we cannot do this. This is the correct way. Okay?
Yes.
First of all, what we have to do, we have to singly fill with the same spin. And if we have more electrons to fill, then we can start pairing. Okay? Okay, for example, let us have the P subshell only. Okay? Okay, fine. I have got. Wait a second, Yuvraj.
What happens, sir?
Somebody is in the waiting room. I don't know. This ought to be here. Rehbar Alam. 11th class. This is. Are you supposed to be here? Okay, let us leave it. Huh. Yuvraj, I have got P subshell. Not give me a choice of number of electrons that you want to fill in the P subshell.
So 5 electrons.
5 electrons. Okay. So 5 electrons. How you will you fill 5 electrons? First of all, you will need this. We'll divide it into 3. We'll
Then
start
we'll
with
fill it with a single with the
yes,
same spin. Then
yes,
we will add 2 electrons of anti-clockwise spin.
yes. Or else, what you can do is you have a choice, complete freedom to start with a downward arrow.
Yes, sir. That was understood. Yes, sir.
Yes, and then you can fill this way. Okay, this is
Yes.
the correct way. Got it?
Yes, sir.
Any doubt till now?
No doubt, sir.
No doubt. Okay. Now this term maximum multiplicity. Okay. What does this mean? What is maximum here? What is maximum? Maximum we will get to it later. Now for the term multiplicity. Multiplicity is a term in English which is called for multiplicity is known for many of same type. Many of same type. So when we are filling the first when we are singly filling the orbital with the same spin, you can know what is many. Many are the electrons. What is the same type? The same type is the spin. We are filling many electrons with the same spin. That is for multiplicity. Now, what is maximum here? For example, in p subshell, if we have 3 orbitals and we have 3 electrons. This will accommodate for half, this will accommodate for half, and this will accommodate for half. And the spin is an additive term, and this will total count to 3 by 2. Or else we can have another case in which we have these electrons in the anti-clockwise direction. Now these will count for minus half, this will also count for minus half, and this will count for minus half. And again, the terms are additive, hence we will get minus 3 by 2. And spin can either be plus 3 by 2 or minus 3 by 2 if we apply the Hund's rule of maximum multiplicity, right? So what is maximum here? The maximum thing here is the spin. This is the case for Hund's rule of maximum multiplicity. If we violate the Hund's rule of maximum multiplicity for P3 for example, for P3 violation of Hund's rule of maximum multiplicity. If we violate it and we write it like this, this is 1 electron, this is 2nd electron, this is 3rd electron. So here we have an upward spin that will accommodate for half, this will accommodate for minus half, and this will accommodate for plus half, right? And the terms are additive. So if we add these two, this plus half and this minus half will cancel out each other and we will get only plus half. Hence we can see that this plus half spin is less than the magnitudes of these two spins when we filled the electrons in accordance to the Hund's rule of maximum multiplicity. And when we violated the Hund's rule of maximum multiplicity, what we didn't get the maximum spin.
Yes, sir.
Did you get this? Are you
So
Praj?
can we go to the previous page?
Oh my God. You have just wasted my monologue, I guess. Yes. What did you have to write here? What did you miss?
Sir, 1 minute. Multiplicity is the many of same type.
Many of same type. What is many here? Many is the electron. What is same type?
And
The same type is the spin. We have
yes,
electrons in the same spin. That is a multiplicity.
done on this page, sir.
Done on this page. I hope you heard when I was speaking in this page.
Sir, if we get P5, then what will be the Hund's maximum multiplicity?
If you have P5.
Yes, sir.
Okay, fine. We will do P5 for both the cases, right? We will do P5. Okay.
Yes, sir.
Do we have any choice here? Like, is there any possibility of violating the Hund's rule?
Uh, no, sir.
No, right? Right?
Yes, sir.
That is what I was saying. If you have plus 5, then P5, then you don't have any other choice of writing the electrons other than this. The only thing here is about P2, P3, right? And also we can in P4 also we have a choice, I guess. Just C. 2, yes, in P4 also, right? In P5 we
Yes, sir.
don't have any choice other than writing it like this. We cannot violate it for P2, P3 and
But sir, what will be the maximum multiplicity? It would remain 3 by 2? Because
no,
sir,
no,
the
no.
positive.
Okay, fine. The maximum multiplicity is the name given, right?
Yes, sir.
It is the name. It is not. It will not be. See, for example, in P5 we don't have any choice. But if we cannot violate the Hund's rule of maximum multiplicity, and we cannot even fill with the accordance of Hund's rule of maximum multiplicity because we have only one choice. We don't have any choice. Hence, the rule doesn't comes here. The rule will come only where we have a choice in these cases.
Okay, sir.
Do you understand?
Yes, sir.
Right. For example, if we say about S subshell and if somebody asks you about the Pauline's exclusion principle, you will say there is only one orbital and we don't have any other choice. But if we have P subshell, then the Hund's rule of maximum multiplicity comes into play because we have now choice of filling the electrons in this orbital or the other orbitals, right?
Yes, sir.
Okay. So a rule comes in only when we have a choice and we have to make a choice. Did you get this?
Yes, sir.
Any doubt till here?
So, sir, Hund's rule of maximum multiplicity is just about the positioning of arrows.
Yes, positioning of atoms.
Atoms, yes.
Positioning of atoms. So where will this help you? This will help you in many questions which asks about let us say application of Hund's rule of maximum multiplicity. They will ask about calculate the number of unpaired electrons in the following. Calculate the number of unpaired electrons in the following. Let us take, for example, Fe. Let us take the ionized form, Fe2 plus. Just take the same metals that we took earlier. You must be accustomed Ni2 plus. Let us take magnesium. Just take Sakti, vanadium, Feconicuzan, DEF, Sakti, Kraman. Let us take aluminium. Calculate the number of unpaired electrons in the following.
Yes.
Let me know if you want the atomic number of any of them.
So I'll need the atomic number of V.
Vanadium, Sakti 23. Others you have, right? You have done this these earlier. Aluminium is 13, magnesium is 12, nickel is 28, Fe is 26. Magnesium is 12, aluminium is 13.
Excuse me, sir.
Done.
1 minute, sir. So I had a general question.
Okay.
Till where should we know the atomic numbers?
Sorry.
So till where should we know the atomic numbers?
At least till zinc, I would say, in 11th, 12th standard. Otherwise, you must know how to make a periodic table. You must used to have the, this is the spelling, right? Mnemonic. You must have some kind of mnemonic to write down the whole periodic table.
So by unpaired electrons, we have to know how many electrons can be there in a subshell, and then subtract it, or just the orbital.
Now, for example, if you have P5, right?
Yes, sir.
So how the P file will look in the orbital picture? It will look like this: 1 electron, 2 electron, 3 electron, 4 electron, and 5 electrons. So you see this. This is paired. This is paired. Only this is unpaired, right? Hence,
So
you
we'll
will
say that
say
we have
one.
one unpaired electron.
Yes, one unpaired electron.
Okay, sir.
And most of the time, you have to just see uh, the ultimate and penultimate. This is the term that usually comes in JEE mains and advanced examinations. Ultimate and penultimate shells. This is just a fancy way of saying last and second last. You just see these two shells and you will know about the unpaired electrons. Usually you have to see the second last shell, that is the penultimate shell, if we have the transition elements and there's an involvement of d subshell. Usually d subshell. The F subshell question doesn't come usually. Done?
1 minute, sir. Uh, so we can have 10 electrons in D shell, na?
We can have 10 electrons in D subshell, right?
So for first part, we'll have 2 unpaired electrons.
For first part, you will have 2 unpaired electrons. Okay, we will see. Please reconsider, I would say.
Oh, sorry, sir. 1 minute. Sir, 2 ही आ रहे हैं.
Really?
Please, sir, can you do 1 for me?
Okay, I will do 1 for you. You remember what we have here? We will have 3d6, right?
Yes, sir.
We have 3d6. So if we have 3d6, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, right?
Okay, sir. समझ आ गया, sir. 1 minute. So in the second one, we will have 2 unpaired.
2 unpaired. Yes, right. This will be 3d.
Sorry, sir.
3d8, right?
Yes, sir.
Then
And then, sir, again 2 unpaired.
for manganese, what will we have? Neon is 10, right?
Yes, sir.
We will have neon comes in the second place. So 3s.
So 3s2.
3s2.
So 0 unpaired back. So 0.
Yeah, true. The S will have both of the yeah. Now
Yes, sir.
vanadium.
So for this we will have just 3 electrons are filled. So 3 unpaired.
Right. The S is filled, right? We will have 4s2 and 3d3.
Yes, sir.
Correct?
Yes, sir.
Correct? So it will be
3 unpaired electrons.
3 unpaired electrons, right? And for aluminium?
So for aluminium we will have again 3 unpaired. Wait a second, sir. 1 unpaired. So I guess there's some issue.
Everything visible, Yuvraj?
Yes, sir, the screen is now visible, but everything got erased. Though, sir, I think the last question was aluminium. So it would be the last shell will be 3p1, so 1 unpaired electron.
This will be neon, right?
Yes, sir.
Then 3s.
So 3s2 and 3p1.
3p1. So only one unpaired
So 1
electron.
unpaired electron.
Only one unpaired electrons, right? So you have noted all the questions now, right?
Yes, sir.
Okay, can you tell me the questions? What were them? What were they? I wait a second. I remember Fe2 plus. I remember Ni2 plus. I remember vanadium and what else?
Magnesium and
Mag-
aluminium.
These are the four, right?
Yes, sir.
There's a concept which is called magnetic moment. Magnetic moment. Okay. How it is
So this concept.
calculated? It is a new concept. It is related to unpaired electrons. Hence, I am adding this here only. Magnetic moment. How do we calculate magnetic moment? We calculate it by under root n into n plus 2, and the unit is Bm. It is known as Bohr magneton. It is the atomic unit for magnetic moment. And what is n here? N is the unpaired electrons. Okay.
Yes, sir.
So you will calculate the magnetic moment for all for these five. 1, 2, 3, 4, and 5.
So first in 15 under root.
First is how much?
15 under root.
Why 15? How 15?
So, oh, sorry, sir.
See.
So 3 under root.
Yes. This will be like this: 1 into 1 plus 2, right? So this will be under root 3 bm. Then you can remember this. Do you know anything about chess?
A bit, sir.
A bit. There is a thing which is called GM. The full form of GM is Grandmaster. There is something called which is IM. IM is International Master. And in chess, if you do a very silly mistake, and in usual language also we call a silly mistake a blunder. So there are some blunder masters. The amateur player who play chess, they do too many mistakes and we call them blunder master. So you can remember BM as blunder master if you are any fan of chess. Now let me erase this. People will think what I am teaching. So what is BM?
Sir, Bohr magneton.
Right, Bohr magneton, not blunder master. Calculate for others.
So for Fe it will be 2 under root 2 bm.
For Fe we had how many? 4, right?
So 2 unpaired.
For
Oh, wait
Fe,
a second.
no, we had 4 unpaired, I guess. It
So I
is
didn't
3D.
change my wrong answer, so that's why maybe 1 minute.
You didn't change your. This will be 4 into 6. This will be equal to
24 under.
2 root 6. We can write it like this, right? You can write it like this. Excuse me. Yes, for nickel.
So for nickel, we had 2 root 6.
2, then 2 plus 2, Now this will be equal to 2 into 4. Now this will be 2 root 2. Right. For vanadium, we had how much? Suck TV. This is 3.
Yes, sir. So
3.
3 into 5, 15 root.
This will be equal to 3 into 5. This is the root 15. Can we do anything to 15? I don't think we can do anything to 15. For Mg, how many unpaired electrons?
So root 2.
How many?
So root 2.
Array root 2. How can root 2 unpaired electrons can be there? I'm asking how many unpaired electrons?
0 unpaired electrons, sir.
If 0 unpaired electrons, see this is where mistakes happen. This is where mistakes happen. You have to
I was
multiply.
telling the answer root 2.
Root 2 is a wrong answer. Na? That is why did I not write 2 root 6, 2 root 2 and root 15? Why did I do all this mathematics here?
Oh, okay, sir. Sorry.
What will be this? This will be 0,
0,
na?
sir.
Root 2, root 2, root 2. 2 root 2, 2 root 2. Start singing that song. Fine. Now we have done magnetic moment. Okay. Noted, na? Noted everything?
Yes, sir.
Okay. You're done with magnetic moment. Now learn something about magnetic moment. What is magnetic moment? First of all, what does it do? It gives the idea about the magnetic character of a substance. So what is magnetic character of a substance? If you take any substance and if you exhibit and expose it to some kind of magnet, it will show some magnetic behavior, right? It will either attract it to one of those poles and it will be repelled by the other pole. So this is the magnetic character that we are talking about. Hence, for now, you don't have to do the experiments and you can just say the magnetic moment character. How? You can say the magnetic character of a substance by seeing the unpaired electrons in a substance. If a substance has unpaired electrons, that is an electron which has not been paired. If a substance has unpaired electron, then it is said to be paramagnetic. It is said to be paramagnetic. What does paramagnetic mean? That is, it means that it will exhibit, fancy way of saying show, it will exhibit magnetic properties. So magnetic properties. Third item. What is the third thing? If a substance has no unpaired electrons, then it is said to be diamagnetic. What does this mean? Diamagnetic. That is, it will show, fancy word for show, exhibit no magnetic properties. No magnetic properties. Any doubts still here?
So magnetic moment gives an idea about magnetic character of a substance.
Yes.
Substance has unpaired electrons, then it is said to be paramagnetic. It will
Yes.
exhibit magnetic properties. If the substance has no unpaired electrons, then it is said to be diamagnetic. It will exhibit no magnetic properties. Sure, sir. Done, sir.
Done. Easy.
Yes, sir.
Okay. Noted. Noted down.
Yes, sir. Noted.
Noted. Okay. Great. So the last topic for today is what we were learning. Do you remember? Before magnetic moment, before unpaired electrons, what was the broad topic?
Sir, we were doing electronic configuration
Yes.
of
Ions. We started with electronic configuration of ions.
condensed electronic configuration. Yes, sir.
We will learn electronic configuration, but we will learn some of the exceptional electronic configuration. Exceptional electronic configuration. Out of the 118 elements in the periodic table, there are 20 elements which, let us choose a fancy word for show. Fancy word for show is what? Exhibit.
Exhibit.
In CBSE, write exhibit 20 times, you will get 20 more marks. 20 elements which exhibit exceptional electronic configuration. What is exceptional? Exceptional is just a way of saying that we didn't expect this. We expected something else, and the actual was something else.
Yes, sir.
These 20 elements, 10 of the elements belong to the D block. Other 10 the remaining 10 belongs to the F block. 10 are from D block, 10 are from F block. Okay, so
Yes,
note this down, and when you have noted this down, we will talk about those 20 elements. First the D block elements, then the F block elements.
done, sir.
Done? Okay. What are those elements? First, this is slide first the D block elements. That's it. D block. How will you remember this? For remembering, there is a mnemonic. Mnemonics will be used very often in chemistry. RU Rhodes. Do you know a player? The name of the player is John T. Rhodes.
No,
Heard
sir.
of him?
No, sir.
Heard of him? Huh?
No, no, sir.
No, okay, you should YouTube about Jonte Rhodes. He was an exceptional player, and similarly, we have the exceptional configuration, and we have RU Rhodes. Okay, RU
Yes.
Rhodes paddles. What does he paddle? He paddles a silver plated, golden cubical car. Golden cubical car mounted as a Nawab. Mounted as a Nawab. What is Nawab? Nawab is the name of emperors that used to be in Kolkata usually.
Yes.
So now we come to what are these elements? This is Ru, simple enough. This is rhodium, which is for Rh. Paddles is will be for palladium. It will be for
Palladium.
palladium, right? Silver is for silver. What is the what do we call silver?
Au.
Not Au, Ag.
Ag.
Yes. Plated is for platinum. Plated is for
Platinum.
platinum. Golden is for
Golden
gold.
Au.
Yes, Au. Cubical will be for Cu, which is copper. The car here is for mnemonic for Cr. Mounted is for Mo, molybdenum. And Nawab is for Nb. Got this?
Yes. Done, sir.
Done. Okay. Now the F block, the exceptional F block. The exceptional F block. Similarly, we will start with LR lace. What is this? LR lace.
Lace.
Yes, LR lace. What did LR lace? This is a name. What did she or he do? Thought. Let me write thought with a capital T. THOUGHT. What did they thought? They thought that your AC is good. Your AC is good. Okay.
So
But what
your is you are.
your is your. She uses WhatsApp or he uses WhatsApp. No, no big deal. Your AC is good. Okay. But CM's PA. CM's PA said no. This will be for LR. This LA and C is made up of two elements, La and Ce, that as the name suggests. Thought will be for thorium Th. Ur is for uranium, but uranium is just shown for U. Ac is actinium, which is Ac. For for good, you just remove the GOOD and you write it GD. Cm is Cm, Pa is Pa, and for nope we have Np. So please repeat this line with me. LR lays thought
LR
your AC
lane. Thought
good,
your AC is
good.
good.
CM's PA said no.
No.
Okay. And you don't have to worry about the atomic number in any examination. If they ask about the exceptional electronic configuration, they will give you the atomic number. Okay.
Yes,
You
sir.
don't have to worry about the atomic number. You just have to remember this and the next thing which I'm going to do. I mean, usually this comes in entrance examination, the exceptional electronic configuration. The only thing that usually comes in CBSE is about copper and chromium, but all the electronic configuration of all the 118 elements now, it has been given in NCERT. And if they have given 118 electronic configuration, including the one those are exceptional, that means they have the authority to ask you about any one of these 20. Okay, so you don't have to think that this is for some competition exams. You will revise this even if you are going for your board examination. Got it?
Yes, sir.
Good. Let me clear this part. Okay, this is what CM's PA said. No. If you have time, I would request you don't mug up the mnemonic that I have given. If you try a bit and try to develop a kind of mnemonic for yourself, then it would be better. This is I came up with this mnemonic in approximately 5 minutes. And why I'm saying this is because I have to come up with a mnemonic in English, in pure English, and I have used just this word, which is a common word for king in West Bengal. So people know this word Nawab. Otherwise, you can come up with your own mnemonics very easily, and that will be easier to remember. Because for now, if somebody sees this, they will be like, "What rubbish is this guy speaking? Doesn't make any sense." Better than remembering this mnemonic, I will remember the whole of 20 elements by their name. But if you come up with your own mnemonic, then it will be easier.
But sir,
Okay.
these are very easy.
These are easy. Okay, I'm glad you found these easy.
Done, sir.
Done? Great. Okay. Now tell me what are those mnemonics, if you remember it. Don't see the book. Don't see your copy.
Sir, are you roads, pedals,
Hmm.
a silver coated golden cubicle car mounted as a Nawab?
You said not coated, it is plated, silver plated. Okay.
Yes, sir.
Right. Then the F block elements, LR.
Sir, LR lace
Hmm.
thought your AC was good.
Hmm.
CM's PA.
Hmm.
So was it head or said or thought?
CM's PA said no.
Said no.
Okay. CM's PA said no. The only things that you have to remember now for the filling of the exceptional electronic configuration, you have to note these points.
So just a question, like order of these exceptional elements matter?
Order, like
Yes.
where they come in the periodic table.
No, so in general, in remembering the order, does the order?
No, the order. There is no such order that I have taken care of. I mean,
Sure, sir.
okay. Even I
So
have
if
not.
I say that LR lace thought, uh, or if I say CM's PA thought your AC was good, and LR lace said no,
You can
that
you can change. There is no problem in changing. You can
yes, sir.
say the CMSPA thing before, and you can say the LR lace thing afterwards also.
No,
And
I just asked it if I have to make my own, so I'll keep this in mind.
okay, fine, that's better. You
Yes.
made very new. I mean, very new. That is very new. You you just changed the arrangement of phrases. I mean, that is exceptional talent. Great. Okay. Listen, what you have to do is you have to remember first of all these two elements in the exceptional case in PD and TH, one from D block, one from F block. Okay, in PD and TH, two electron transfer takes place. Okay, fine.
Yes.
Second, in the remaining 80, one electron transfer takes place. Fine. In PD and thorium, how many electron transfers take place? Two electron transfers. In the remaining 18, how many?
Electron transfer.
One electron transfer takes place. Okay. Now you will get two cases. As I said, there are two lists. One is for D block and one is for F block. So if you will have anyone from the D block, you will see that if S and D subshell are present, if S and D subshell are present, then electron will transfer from S to D. Okay.
Yes.
But if F and S are present, or S and F are present, that will be most probably and most prominently in the F block element. If S and F subshell are present, S and F subshell are present, then electron will transfer from F to D. You just have to remember these 4 points and the two mnemonics that
F subshell.
Sorry?
Sir, S and F subshell.
Yes, S and F subshell will be present somewhere. Because if you remember the sequence, how do we write it? N, S, again, this thing will come each and everywhere. N minus 2 F, N minus 1
P, NP.
and NP, right? So for example, if you have, let us say 6S, right? 6S, and then what you will write? You will write 4F, 2, and for example, let us say 10. If you have to fill only 12 electrons, you will not go to the N minus 1D, right?
Yes.
Right. So S and F can only be present also, but the D subshell, that is 5D, it will be present, but it will be vacant till now. And if this electronic configuration is in one of the elements from the 20 exceptional cases, now this F, the 10 electrons from F will transfer to D electrons. First write this, then we will do some examples. You will get a better picture. It will be very much sluggish now.
Done, sir.
You have noted this down?
Yes, sir.
Okay. So let us take, for example, let us take PD, palladium. Let us take PD. First, we will do the exception PD. The atomic number of PD is 46. Write the electronic configuration. It is 46. The noble gas will be?
Sir, Kr.
Krypton. Krypton is 36. You are remaining with 10 electrons. Just remember this. NS.
So 4d6.
How much?
So 4d6.
There is no S.
Sir, obviously 5s2 and 4d6.
Google say about this. 5S,
5s2
5S2,
and 4d6.
4D6,
6.
right? So now, first of all, in the note, read the first line that I have written. What did I write in the first line?
So in PD and TS, 2 electron transfer take place. So sir, I guess that
Okay, now read the third statement.
so if S and D subshell are present, then electron will transfer from S to D. So sir, it will become PDKR 4D8.
Yes, this will be KR. This will be 5S0
0 4D8.
4D8, right? So this,
Yes.
what is this? This is expected. Expected. We expected this configuration, and this was found. So this is called actual, right?
Yes, sir.
Now for thorium. Now for thorium. Thorium is 90. 90. So we'll have the 86 one. What is 86 one?
So
Read on.
6 one is read on, and
Hmm.
so we will have 7s2
7S2.
and 5f2.
5F2. Okay.
This will be expected, but the reality one will be 5f. Wait a second, sir. F to D. So, sir, reality will be 6D2. 7s2, 6D2. Yes, sir.
I mean, I have written as 0, and I have also written 5F0 here, but you can omit these. Don't have to write these. I have just written it here so that I can show that I can show the F electrons has now transferred to the D subshell. Okay, the F electrons are now in the D subshell. Just for that, I have written F0 and 5S0. Okay, this is actual. Now, the most important one for your board examination, which comes usually, which is chromium, Cr, this is 24, and copper, this will be 29. Both will be what? Noble gas, argon, right? Both will be
Yes,
for argon.
sir. 4s, 4s2,
Actual,
3D.
what are you telling me about actual or expected?
Sir, expected.
This will be expected first. Okay, yes, expected. This will be
So it would be 4s2, 3D, 3D4. So this would become AR, 4s0, 3D6.
actual will be AR. How much? 4S0.
4s0, 3D6.
Okay, fine. In the note, there are how many points? 4 points,
Yes, sir.
right? In the first two example, I dictated what
Oh,
points.
okay, sir. Sorry. 4s1, 3D5.
You know, this is something happens. Like if any one of my student comes, sir, this I have this doubt, and most of the time they have misread the notes or they have just ignored something from the notes. Otherwise, you don't have any chance of doing mistake if you read the note properly and apply it to the questions, right? Now
Yes.
firstly, you copper.
Sir, AR, 4s2, and 3. 3D 3D9. So this would become 4s1 3D10.
Actual is Argon 4s1.
So what
3D.
happens when we have the P subshell?
What will you have? You don't
Like
have any
if,
in the P subshell.
okay, so it remains untouched.
It remains untouched. There is nothing in the P block elements. There is no exception in the P block element. Okay. So CR and CU, these two are important. Why? First of all, the other 18 are also important, but these two are important because the reason for them, the exception is given in NCERT, and these reasons are also asked. Okay, so first of all we will see that what are the reason, then we will explain the reason. Okay, reason or cause for exceptional electronic configuration. First reason is, first of all, let us take these two elements, right? We have this. So sometimes it be this and this. Okay.
Yes, sir.
Just remember this. What are these? This is AR 4s1 and 3d5. We have another AR 4s1 and 3d10. First of all, the reason is the symmetric distribution of electron. First reason is symmetric distribution of electron. When the expected was seen, what is expected? Expected is AR 4s2 and 3d5. No, 3d4. The expected one was 3d4.
3, 4.
Right? In this we have this 3d4 as unsymmetrically filled. Right? But argon 4s1 and 3d5, this is symmetrically filled. And in nature, symmetry leads to stability. And the same is true for the electronic distribution. Okay. So if the electrons are distributed symmetrically, that is, if we have 3d5, how will the d subshell look? 1, 2, 3, 4, 5. Each orbital will be
So you're not audible.
Wait a second. What about now?
Yes, sir, better.
Okay. So this is symmetrically filled, and hence